In this tutorial, we're going to dive a little deeper into some of the specific kinds of geometry that Rhino and Grasshopper use, in particular curves and surfaces. There are a lot of concepts that kind of relate between the two of these. So let's talk about curves to start with. Go ahead and hide all of this. I'm going to draw a curve here in Rhino. Curves are mathematically constructed in Rhino. They're what's called NURBS curves. Rhino is a NURBS modeler. NURBS stands for non-uniform rational B-splines. There are other variants of this, but that's generally the gist. And NURBS is effectively the sort of mathematical formula that calculates the smooth stuff on the basis of these control points. So there is a sort of mathematical formula that defines with effectively infinite precision where every point along this curve lies as a function of the location of these control points. Curves can also have different degrees. And so you can see when I create a curve, I can specify the degree. The higher the degree, the smoother the curve will be, but the further it will be from my control point. So I have to really, really work if I'm drawing a degree 11 curve to kind of create some shape. Things are going to be very removed from that distance. And on the other hand, a degree 1 curve is basically just a polyline. In that case, the curve will actually pass through all of the points that I draw. NURBS is more complicated even than that. In addition to the control points, there are sort of not vectors and other things that I don't even really understand the mathematics of. But in practice, you really only ever need to deal with polylines and degree 3 NURBS curves. If you want something smooth, you probably want a degree 3 curve. There are very rare occasions where you would ever want to do something different. And we can draw these by specifying their control points, or there's another way, which is with the interpolate curve, which will allow us to specify points that the curve actually passes through. But you'll notice that if I turn on the control points for this curve, which show automatically in Rhino 6, they're not the points that I clicked. So it's still using this control point representation underneath. These are both NURBS curves. So let's go ahead and launch Grasshopper, and let's look at some of the tools that are available to us in curve and surface. One of the key concepts is that curves can be thought of as bent number lines. Now, what do I mean by that? If you think about a number line, so in fact, let's go into a different viewport style and let's turn on our world grid. We already know that we can specify a point along the x-axis by its coordinates. So, if I want to construct a point and I want to specify its position, I can do so with Grasshopper. Now I'm going to get a point at 5. So we can think of this axis as like a number line where every number represents a point along that line. With a curve, it actually operates the same way. Every NURBS curve has a domain, which is basically a number that represents the beginning and a number that represents the end. And every point along that curve will lie somewhere in between those two numbers. So we can refer to any point along the curve by using a number. And we call this its curve parameter, or sometimes its T parameter. So a really important component and a really important concept when working with curves in Grasshopper is evaluate curve. So evaluate curve lives under analysis. It's the one with the little lowercase t. And let's see what it looks like when I grab this curve and reference it in. As we saw in a previous tutorial, if I want to make a reference to a piece of Rhino geometry, I can go grab a curve parameter, add it to the canvas, right-click and choose Set 1 because this is pre-selected. It should load it in directly. I can see it selected because it turns green when I click. And if I plug this in and then specify a number, I'm just going to use a slider here, I will get a point somewhere along that curve. Now, the first thing that tends to trip up Grasshopper beginners is the question, why is my point all the way over there? How do I know what the domain of this curve actually is? So when we look at this, One thing we can do is actually find the curve's domain. And a quick shortcut way to do this is to convert the curve to a number. I've mentioned in previous tutorials that Grasshopper tries to do something intelligent for you when you convert it from one type to another. So actually, I don't mean a number. I actually mean a domain, which is its own data type. So if you convert a curve to a domain and look at it with a panel, you'll see that you get a representation of its domain. And in this case, the curve that I drew has a domain from 0 to 111.993755. Now, why is that? It's an absolute mystery. No one knows. No, that the reality is that it is some function of the NURBS mathematics that underlies this thing, but you can kind of never count on knowing what the domain is going to be. It's generally a good bet that it will start at 0, but it's not necessarily just the curve length. This curve has a length of 79.5 units, which obviously is not the same as the domain that we've set up. And I think if you'll find that curves with more control points, I'm not actually totally sure this is true, but let's just try making a curve of similar length with a bunch more control points. I think we may find that its domain is actually a fair bit larger. This could prove me to be a liar, but let's just check it out. That one has so I guess I don't know what I'm talking about it because that makes it shorter, not longer. But in any case, the good news is you don't actually need to worry too much about the specific domain, because in Grasshopper, what we do almost always is we transform the curve's domain so that we can reason about it in a consistent way. I want to be able to always know what the domain of a curve is, so that if I put in a number like 50%, I can get in the middle of the curve or whatever. And this is exactly what we do. There's an operation that you can do on any curve parameter, which is to, and by parameter, I mean either this object or any of the inputs that contain a curve. I can right-click it and choose reparameterize, which is a big fancy word, but all it means is reset the domain of this curve to be between 0 and 1. And we do this so that we have a predictable expectation of the domain of this curve so that we can do things with it. So now that I have reparameterized it, when I have the value 1 in my evaluate curve, it's all the way at the far end. If I'm at 0.5, it'll be somewhere in the middle. And if I'm all the way at 0, I'll be at the far end. Now, it is important to notice that just because you specify 0.5 doesn't mean you're literally in the length midpoint of a curve. If you're dealing with a line, that's usually a safe bet. So if I make this line, you'll see that 0.5 is very close to the line. But it is a function of the control points. So I'm going to try another one of these guesses about control point behavior, and I'll probably be wrong again. But if I put a bunch of control points over here, and then have one right here, and load this curve in, then even though I'm at 0.5, I'm still somewhere in the middle of these kind of early control points. So if you're at 0.5, I would roughly expect that there are going to be about the same number of control points on one side as on the other. But again, that's not like a super predictable expectation. So if you need an absolute midpoint, there is a component that I think was added fairly recently in the grand scheme of Grasshopper history called curve middle, which I believe will actually find something closer to the length center of a curve. And so this should give me a more predictable value if I pick this one. This is the length center or the midpoint, and this is the evaluated point at 0.5. And there are various tools that allow us to do things like evaluate at a particular length. So where I'm using evaluate curve, I'm using the curve's parameter. You can even see in the speed that this moves that it's not evenly spaced out, the parameter space of this curve. But if I do evaluate length, I can be more precise. And in fact, evaluate length has a mode which is on by default, which normalizes this length factor. So if I make another slider at 0.5, this is going to basically measure along the length, but renormalize it, which is sort of similar to reparameterizing, to be in the domain from 0 to 1. So if I go from here to here, now I have a point that's evenly located along the length, ignoring the parameter space. And if I turn this off, it will use actual length. So if I know that I want to be 30 units from the end of the curve, I can specify 30 and it will actually measure that. Now, you can also wind up in scenarios where, maybe you go too far or past the end of the curve, in which case this is going to give you an error saying the length factor cannot, this probably means cannot be larger than the length of the curve. So just something to keep in mind. For many use cases, I end up just using evaluate curve and assume that my control points are reasonably evenly spaced. But if I need to be more dimensionally precise, I'll use something like evaluate length. Another way to visualize this kind of parameter thing and the sort of spacing of control points, let's take all my curves and load them into a new parameter. I just did that by double-clicking, typing curve or CRV as a shortcut, and then creating this parameter on the canvas. If I use one of the components from the divide submenu of the curve tab, I can actually evenly divide this curve. So if we use divide curve, and I say, give me, let's say, 20 points along this curve, I can tell by this that it's actually not just evenly spacing the parameters. It's actually doing something on the basis of the curve length. And in fact, the description says this. It's dividing a curve into equal length segments. If we wanted to visualize the parameter spacing, instead we could do something like create a range. We've seen before this component that creates a numerical range of evenly spaced values. And if I were to use this in tandem with evaluate curve, we would see more irregularly spaced points. So if I turn this preview off, even if I do reparameterize it, you can see that these are all equal in the domain of the curve. When I should only be looking at one curve at a time for this. These, as far as the curve is concerned, these are sort of equally spaced in its parameter space. But in general, you'll get something that's like reasonably evenly spaced. And if you want something more precise, you can use something like divide domain. And this will actually output the parameter locations of each of these evenly spaced points. So that's something to note too, is that we can use t, this idea of a t parameter along a curve's domain, as an input to find a point, but it's also often a piece of information we get back from other things that we do with curves to tell us about a position along a curve. So that's just something to keep an eye out for. One example of this is, what if we want to find the closest point on a curve from another point? So this is the curve that I have loaded in. I'm going to specify another point. I'm going to use a parameter. I'm going to grab point. I'm going to say set one point. And in this case, I'm going to use coordinate mode. We'll see why this is in a second. This means that I'm not actually selecting a point object drawn in Rhino. And it has the added benefit, if you have I believe it is gumballs turned on under display, then you can actually move this point directly in the viewport, even though it's not a real Rhino object. This is the one exception where something in Grasshopper can be interacted with in the viewport. So if I have this point and I have this curve and I want to find the closest point to this point on this curve, I can use curve CP, or closest point, and it's going to find the point that is closest. And so I could do something like, draw a line between those two things. But it's also going to output the curve parameter. And because my curve is already reparameterized, we can see by this icon, I know that that value will be between 0 and 1. So now, as I move this around, we can see this value change. It's kind of going to give me back information along the curve's length about where it found that closest point. So this is really useful. It winds up being like a really quick way to get points out of curves, or to just sort of analyze information at a curve. If I want to know something about, the curvature at a particular point, it might be useful to supply it at a t parameter. So if I have my curve and I want to know about its curvature, and I want to know about its curvature at a specific point, I can't just supply that point. instead I'm going to supply the t parameter. So oftentimes you'll need curve closest point to sort of translate from some point in space to a point along a curve so that you can do other things with it, like analyze its curvature. Now, this metaphor of the kind of curved or deformed or stretched number line winds up being even more useful when we start talking about surfaces. Because in the same way that we specify 2D points using x and y coordinates, and we can treat a parameter along a curve as a t parameter, when you extend this metaphor to 2 dimensions, and in order to visualize this, let's just model a surface real quick. I'm going to use surface from points. Something like this. This can be thought of as 2 distorted number lines, or a sort of distorted grid. So, and let's make this a little more interesting. Maybe we'll bend this surface using the bend command in Rhino. Now we have something a little more interesting. One of the concepts you may have seen in Rhino is this idea of the isocurve. You probably have been more interested in just turning it off in the display because it looks bad in your drawings, but the reality is that the isocurve is also a really important piece of information. And iso means same, and what an isocurve is the curve where the parameter along a particular axis is the same. So when we talk about surface parameters, instead of t, we talk about u and v. So every surface in Rhino has a u direction and a v direction. And if you turn on, I believe it's the dir command, you can see these little axes, and it maps very well to x and y. So where in normal Rhino world space, x is red and y is green, in surface space, in the kind of localized, distorted coordinate system of a surface, you have u in red and v in green. And you can see that I can sort of, as I'm looking at the direction, it's going to show me a little preview of the u and v directions of the surface at any given point. The other thing we'll see is that if I turn on the control points of the surface by hitting F10, and I distort these things, it's going to be similar to when I was moving the control points around to the curve. So, even something that has roughly the same kind of boundary shape may well have a more distorted geometry internally as a function of its control points. So let's look at how we do some of the same things we were doing before with our curves with a surface in Grasshopper. So I'm going to reference this surface in under params. I'm going to grab a surface and set 1. And now I have a reference to it. And just like we evaluated the curve, we can also evaluate the surface. So under surface analysis, we're going to find this one, which looks like a little point along a sphere, or half a sphere. We're going to evaluate the surface, and it's asking for a UV. And if you hover over it, this was something that took me a while to understand in Grasshopper. It's actually asking for a point. And a point, in this case, is not representing a point in world space. So, but we can see that because of this little black hexagon with the X, we can see it's actually the same data type as a regular old point. So even though we're not representing a point in world space, we're representing a point along this distorted two-dimensional coordinate system of the surface, we're still going to use the same type of object to represent it. So we're going to construct that UV point just like we would construct an XY point. So if we go to vector and point and say construct point, I can plug this point in, and this point is by default at 0, 0, 0. I'll also put some sliders in here and copy and paste. And you'll see that as I move this point, it has two locations. It has the location that's being generated here, which is the coordinate at 0.5, 0.3 over here near the origin. But when I pair it with evaluate surf, I'm also getting its point within the coordinate system of this surface. So one thing you'll notice right away is that we're very close to one corner. And just like a curve has a domain, a surface also has a domain. In fact, it has a two-dimensional domain, which is a specialized data type that we'll often be dealing with when we work with surfaces. So if I go look back here, in addition to domain, there's this domain squared, which represents a 2D domain. And the same way that converting a curve to a domain told us about its curve domain, converting a surface to a 2D domain tells us about its UV domain. So we can see in the representation here that the U domain is from 0 to 93.9, and the V domain is from 0 to 93.08. Lord knows why that is exactly, but we don't want to worry about it. We want to have a predictable representation of the surface's domain, and we're going to do that in exactly the same way as we did with curves. We're going to right-click a parameter that contains a surface and reparameterize it, which resets its domain to be from 0 to 1 by 0 to 1, and then allows us to know that 0, 0 is going to be one corner, 1, 1 is going to be an opposite corner, and 0.5, 0.5 is going to be somewhere in the middle. It's not guaranteed to be the absolute area centroid of the surface, and in fact, there are many different ways to think about what the most meaningful center of a surface might be. But in general, it doesn't matter too much. So we can see that, as I move this and the x is constant and the y changes, it follows this isocurve, which is iso along the u-axis. It's where u is equal to 0.5. So we can also extract these isocurves ourselves. So in addition to them just being something we display in Rhino, we can turn them off here. We can use them as geometry in Grasshopper. So under Surface, Analysis, we can go get the isocurves. I believe this is where these live. I guess not util. There we So much for that. You can tell that I really have no idea where stuff lives in the menu because I always search for it. Let's find out where it actually was. It lives under curve. So there you go. In any case, just like evaluate surface did, Isocurve expects a surface and a point representing a UV coordinate. It can take a little getting used to this idea that we should be constructing this sort of virtual geometry. It's but this point doesn't matter. All it is a way to represent this kind of set of coordinates, even though it doesn't physically have anything to do with this point at 0.5 and 0. Over here. So usually what we do is when we're constructing a piece of virtual geometry like this, we just turn off its preview. It's, we're using it as data, but we're not using it as real geometry in the world until we do something with it. Now, this isocurve component is going to give us back two curves, one in the u direction and one in the v direction. And I'm just going to create some curve parameters and plug these in so we can visualize it. And you can see that as I change the y coordinate, I'm moving the location of the u curve. And as I change the x coordinate, I'm changing the location of the v curve. And if we want to get, a spaced out range, often I'll want some kind of an isocurve grid over a surface, not dissimilar to what we can see in the Rhino preview. So in that case, I'll just provide a list of points. So the way we create a list of points, I think we've seen before. I'm going to create a range, a numerical range, and I'm going to plug that in to be the numerical input to this point component. So instead of providing this slider, I'm going to create a range of x values. And I could even use that same range for my y values. And what that will do, you can see what that is doing is it's evaluating these points. I'm going to turn on this only draw preview for selected objects so we can just look at these points directly. It's creating this series of points that kind of follow the diagonal from 0, 0 to 1, 1 in the surfaces domain. and then grabbing the isocurves that stem from each of those locations. So I'm going to get all of the curves in the u direction and all of the curves in the v direction. One more important point about surfaces that I think trips up beginners is that Rhino and Grasshopper are slightly different in their terminology. And in fact, there's a subtle distinction under the hood between a surface and a polysurface face, or a BREP face. So what do I mean by that? When we construct a surface that, when we construct like multiple surfaces that join together, like if we make a box, this will actually make an extrusion, but it's the same general concept. We have a sort of poly surface. And in fact, if I explode it, we'll see that now we get the component surfaces. If I join these back together, we'll have a poly surface object. And so under the hood, Rhino distinguishes between surfaces and polysurfaces. And it calls polysurfaces BREPs, or boundary representations. So first, you'll see the word BREP show up in Grasshopper. So this thing, some people call it Brep, although that drives me insane. But, you know, be my guest. So the BREP doesn't necessarily have to include multiple surfaces. And this is where things vary, yet again, between Rhino and Grasshopper. Because sometimes you can draw a shape. Let's just try this. I'm going to draw a sort of a funky shape. And I'm even going to put like a hole in the middle of it. And if we construct a surface from this in the Rhino context by using planar surf, we get an object which Rhino calls a surface, and it's even Grasshopper will let us refer to that as a surface. However, the truth is that this is not a surface. What do I mean? In Grasshopper speak it is, but in the reality of surface mathematics, all surfaces have exactly 4 edges and are always effectively deformed rectangles. In the same way that like a curve is just a deformed line, a surface in Rhino's sort of internal mathematics is always a deformed rectangle. So we can see that when I click on this and say turn on control points, these control points actually describe a rectangle. And the isocurves of this surface, and I'm actually not sure what will happen if we plug this guy in. I think the isocurve component is smart enough to trim these curves for us automatically. But when we evaluate these points, they may well live outside of the surface. Because in fact, what this object really is, the thing that Rhino and Grasshopper both call a surface, is in fact a special BREP that only has one face. And the reason why this matters is that a BREP face can have what are called trim objects, which is information about the boundaries of that geometry. And so the reason we can create an object with an arbitrary number of sides is because we're actually creating a full surface. And we can see this if we run the untrim command on this guy. Let me just make a copy over here. If we say untrim, I can untrim any of these edges and get back the real surface that was there all along. But Rhino and Grasshopper will hold on to the trim information, which is basically like, okay, let's hold on to a set of curves as well, which tell us what parts of this surface to exclude from our geometry. So that's probably a little more advanced than you need to worry about at this point. But one of the things that I often see is that students get confused when they want to be dealing with surfaces, and all of a sudden they get back stuff that lies well outside of the surface. So it's important to keep in mind that, and actually we can see this even more extremely if I rebuild this surface to have more control points with the rebuild command. These control points actually exist. And even though they're outside of the domain or outside of the trim regions of this special single face B-rep. So that's just something to keep in mind. And you may find that as you're dealing with surface coordinates, you can always guarantee that there will be a U-axis and a V-axis. It's just that part of that might lie outside of the trims of that surface. So I hope that's somewhat clear. So that concludes our tutorial on curves and surfaces.